I talked yesterday morning about the impact of climate change in a sort of more physical, biological way. I also talked about economic valuation methods, and now I'm going to apply this stuff to the economic impact of climate change. So I did show you this slide, scenarios on the left, reasons for concern on the right, and I'm going to focus first on the middle bar, no, the bar that is further to the right, that is what is the impact of climate change on the welfare of the median person on the planet. And then I'm going to talk about later about the distribution of those impacts. You're looking at here are all estimates of the total economic impact of climate change. Those are the blue dots. And the way to read this graph is that on the horizontal axis we're looking at scenarios of climate change, here indexed by the change in global mean surface air temperature relative to pre-industrial. So we go for the origin, right? No change, no impact, by definition. And as you see, people have reported these things for a mild cooling of 1 degree up to relatively severe warming of 6 degrees. So that's the horizontal axis. And then the vertical axis is the welfare equivalent income loss. So one way of reading this graph is if you focus on the 2.5 degrees, is that a global warming of 2.5 degrees Celsius would make the average person feel as if she had lost 1.1% of her income. And 1.1 is the average of the blue dots around here. So that is the information that is contained in this graph. First question that you might ask is, where did these numbers come from? What methods did people use? By far the most common method is the so-called enumerative method, which is roughly what I did yesterday. That is, you come up with a list of the impacts and quantify them in their physical units, the biological units. You estimate the price. That's sometimes easy if we're talking about things that are traded on markets. It's sometimes hard if things are not traded on market. You have the impact, you have the price, you multiply the two, you add them all up, and then you have a total welfare. Simple as it may sound, wrong as it may sound, it does not even include partial equilibrium effects, but if you have a large quantity shock, you would have expected the price to change. Simple and wrong as it may sound, this is by and large what the majority of the literature has done, and definitely the more famous studies in the literature have done. Other people have used computable general equilibrium models, not just partial, but general equilibrium models. It roughly works the same way. That is, you start with a list of the physical impacts, you put them into a model of how markets operate, and then you estimate total welfare change. That's the advantage that price responses are included. That's the advantage that interactions from one market to the other are included. Some of these interactions are pretty big. For instance, a number of the studies that have used the enumerative method first estimate the impact of climate change on agriculture, and then separately estimate the impact of climate change on water resources, value the two of them, add them up, ignoring that 70% of freshwater use is in agriculture. These beautiful general equilibrium models at least have some sort of semblance of internal consistency there. Problem with computable general equilibrium models is, of course, that they're good at things that are traded and not so good at things that are not traded on markets, or in fact, they omit those things altogether. And there's a few studies that do this. Yet other studies use statistical or econometric methods. What people have done there is that they've estimated the relationship between something that is of relevance and the climate over space, and then assume that this relationship holds over time. The first to do this were Mendelssohn, Nordhaus, and Scholl. And essentially what they did was they ran a regression of agricultural land values against climate controlling for all sorts of other things that might affect the value of agricultural land. And this goes back to David Ricardo's work, of course, who says that everything that is relevant to the value of an asset should be reflected in its price. And of course, if you buy a piece of land, you also buy the climate in which that piece of land sits, right? And as climate affects the yields of the crop that you might think of planting there, climate is relevant, and therefore the climate should be reflected in the price of the agricultural land, which is exactly what they find. And there's in principle nothing wrong with what they've done, but they did take a bit of a leap of faith when they said, well, we've estimated this relationship over space, and we assume that this relationship holds over time. Why is that a leap of faith? Well, actually for two reasons. One is markets, both over space and over time, but markets are much stronger over space than over time because it's fairly easy to travel through space. It's fairly easy to ship foodstuff over space, and you can do it in both directions, right? Time you can travel only at a constant speed in one direction. So intertemporal trade is much less common, definitely in stuff that terraces fairly rapidly, much less common than trade over space. So that is one assumption that it makes. That is a bit peculiar. And the other thing is that they did this actually for the United States, that over space, technology is relatively constant, institutions are relatively constant, but that is the same is not true over time. That is what people have done, and then this sort of study has been repeated for other indicators of economic activity and its relationship with climate, and then consequently ergodically extrapolated over time. A few other studies have directly looked at self-reported well-being and its relationship with climate. Also found that people in warmer climates tend to be happier. Everything else held constant. Unless it gets too hot, and then they get less happy again. And this relationship is then also applied over time. The last thing, the final thing that one of the papers has done, and there's another paper in the making, is to just ask experts, what do you think the impact of climate change would be on economic welfare? It's a simple method, not necessarily a valid method. The guy who did it, Bill Nordhaus of Yale, did it in 1993, at which time you could arguably make the case that there weren't any experts around, right, to interview, because nobody had ever done it. So the question is really, so what were these guys experts in? Of course, we're also in interviews. Anyway, this is what people have done, and here are the results. There's actually a fair number of messages that come out of this graph. The first is, if you count very rapidly, then you would see that there's only 27 blue dots here. That's a thin empirical basis for any conclusion. You would have thought that the people going around the world saying that climate change is the biggest problem of humankind, or at least the biggest environmental problem of humankind, then you would say that there must be a lot of evidence backing that up to make such a dramatic statement. That's not the case. There's been very few studies. And it's not just anybody who's traveling around the world saying those things. A couple of months ago, Christine Lagarde, the head of the International Monetary Fund, was interviewed and asked the question, what keeps you up at night? And he said, climate change. Not structural imbalances between China and the USA, not the Eurozone, and the complete message in, no, climate change is keeping her up at night. You ask John Kerry, the Secretary of State of the United States, what is the biggest problem? He says, climate change. If I were John Kerry, I would not know what is my biggest problem. Is it Nigeria? Is it Libya? Is it Iran? Is it Iraq? Is it Russia? Is it China? Maybe it's Venezuela, right? If you ask Ban Ki-moon, what is the biggest problem of humankind? Secretary General of the United Nations, he would say it's climate change. Right? Now, if you believe these numbers here, then a 2.5 degrees global warming would cost about the equivalent of 1.1% of income. Now, 2.5 degrees of warming is something you could expect over a period of 50, 70, 80, 90 years. 1% of income change is something that you would normally expect in 6 to 12 months. So, say, roughly a century worth of climate change is equivalent to roughly a year's worth of economic growth, losing a year's worth of economic growth. This doesn't suggest that this is the biggest problem of humankind, right? I mean, if you ask the Greeks, rather climate change or the euro, I mean, they lost 25% of their income between 2008 and 2012. So that would suggest that it is a bigger problem for them than a loss of 1%. If you ask the people of Syria, would you rather live in Syria or in Greece, they would probably answer, I'd rather be in Greece, right? I'd rather lose a quarter of my income than having my entire country shut to pieces. So we can be very cynical. Why does John Kerry say this, right? Why does Christine Lagarde say this? And the cynical explanation is that the problems that are within their mandates are not problems that they actually can do a whole lot about. So therefore they prefer to talk about problems that are outside their mandate and pretend that these are much bigger problems than the things that they can actually be held accountable for, right? That would be a cynical explanation of the statements of Lagarde and Kerry. Not that I would want you guys at your young age to be so cynical, right? So that is the first message, or the second message that's come out of this, right? The first message is the empirical basis is thin. The second message is that the impact of climate change, as far as we know, do not support any dramatic statements such as climate change is the biggest problem of humankind. The blue dots are comparative static estimates. What would the impact of climate change be? The red graph is essentially a fitted curve through this. This happens to be the curve that seems to fit best at the moment. And that suggests that a little bit of warming is probably good for the average person on the planet. There's 3 reasons for this. One, warming would lead to a lot of savings in terms of energy expenditure in winter. Warming would also avoid a lot of cold-related deaths again in winter. And thirdly, warming is driven by CO2, and CO2 fertilizes plants and makes them more water efficient. So we also see improvements in agriculture. But then as the place gets warmer and warmer and warmer, the negative impact of climate change starts to dominate. These initial benefits are no ground for subsidizing greenhouse gas emissions, because they're sunk benefits. Actually, what you see here is that the turning point is at around 1.2 degrees of warming. We've already seen 0.8 degrees of warming. There's a lot of momentum in the ocean. There's a lot of momentum in greenhouse gas emissions, because they're driven by the energy system, which has a lot of momentum. And there's also a lot of momentum in the politics that would reduce those emissions or set the signals to actually start reducing those emissions. And all of that together implies that we'll be kind of warm by another degree, probably another 2 degrees, maybe there'll be another 3 degrees before we start turning. So these initial benefits that we see are essentially sunk benefits. regardless of what we do with our emissions, this climate change will happen, and therefore it should not affect our decisions. Now, to see if this curve is correct is that from 1.2 degrees warming onwards, things are turning down. Of course, what matters is not where do the impacts become negative, but where does the incremental impact become negative. And no policy in the world would get us there. So the incremental impacts are negative over the domain that matters for policy. I've lost count. This was the fourth message from this round, I think, but maybe the fifth. The final thing I want to talk about is the uncertainty. We again focus on the 2.5 degrees, and then we find remarkably that people agree on the order of magnitude of the impact, a percent of GDP or so, but cannot agree on the sign. That is, some people say that this would actually have still have a positive impact on human development. And indeed, if we sort of take the red dotted lines, which is an estimate of something that you may consider to be the 95% confidence interval, then we would see that the impact of climate change do not significantly deviate from zero until we hit about 4 degrees warming. The uncertainty is also asymmetric in the sense that if you look at the distance between the solid red line and the thin red line, the dotted red line, you would see that the upper bound of the confidence interval is much closer to the mean than the lower bound of the confidence interval. That is the structure of the problem. If we look at the climate sensitivity, that is how much would the world warm if the concentration of CO2 in the atmosphere were to double, then we would find that the best guess is around 2.5 degrees, with an uncertainty ranging from 1.5 to 4.5. 2.5 in the middle, 1.5 at the bottom, 4.5 at the top. So that is already asymmetric, and negative surprises are more likely than positive surprises of equal magnitude. If you look at emissions, it's easier to imagine a world where people burn lots of fossil fuels, where China turns to liquefaction of coal and perhaps underground coal gasification, rather than a world that rapidly moves towards renewables. It's easier to be pessimistic about emissions than optimistic. Most of the impacts of climate change are more than linear in climate change itself. A doubling of warming would not lead to a doubling of damage, but more like a quadrupling of damage or more. And then if you consider the knock-on effects, it's easier to imagine a world that is severely damaged by climate change than a world in which everybody becomes blissfully happy because of climate change. In fact, nobody has seriously suggested this ever in the literature, as far as I'm aware. Whereas the sort of the negative scenarios, the downsides, people actually easily talk about them and they seem to be vaguely plausible. One example of that is a scenario as follows. So climate change, sea level rises. Bangladesh is a very low-lying country. 1 meter of sea level rise without additional coastal protection would mean that we would have to evacuate 30, 40, 50 billion, million, don't overdo it, 30, 40, 50 million Bangladeshis. That can be moved, right? Some of them would move into the hills of Bangladesh. It's a less densely populated, but populated by different tribes. They don't really like each other, the Bengali and the people up in the mountains. And there is already a lot of tension and occasionally low intensity civil war going on in Bangladesh. Chances are they won't stay in Bangladesh and they will spill into India. There's been a lot of tension between India and Bangladesh ever since 71. So you can imagine that an influx of 20 or 30 million Bangladeshis into India would not go down very well. You can imagine that would escalate into violent conflict. And you can imagine that then the Pakistanis would come to the rescue of their Muslim brethren, right? And then you're talking about nuclear war on the Indian subcontinent. And you can sort of like come up with a chain of events that is not implausible, right? Nothing of what I said is not very likely, but nothing of what I said, you can definitely rule this out. This will never happen. So the negative consequences of climate change have this downside risk. And it's very hard to say that we go beyond, we go to here but not further. Right? You can paint pretty bleak pictures of the future with climate change. But you cannot say, because of climate change, everybody will be rich and happy. There's no causal chain of events that would lead you to that conclusion, I don't think. So that means, right, that the downside risks are much larger than the upside risks, and that is exactly what you see depicted here. If you start taking these things into account, then perhaps climate change is equivalent, or a century worth of climate change is perhaps equivalent to losing a decade of economic growth, rather than a year, as I suggested previously, and as suggested by the media. All sorts of things wrong with these studies. The assessment is incomplete. For instance, people have still not included tourism in the whole thing, even though it's pretty obvious that tourism would be quite severely affected by climate change. Not necessarily negatively, but you could expect large impacts there. Interactions between impacts, as I said, are not necessarily included the way you would want to do them. People make pretty strong assumptions about adaptation. A lot of the impact literature, as I said yesterday, assumes that people are incredibly stupid and keep trying the same thing, even though there's now been shown for 50 years that it doesn't work. Other studies assume that people are incredibly clever and very well informed. That is a perfect foresight of the climate, and they operate in a perfect market, and therefore the impacts are fairly small. Those are the two easy assumptions to make. Reality lies somewhere in between, but it's much more difficult to model or to quantify. People tend to focus on sort of the middle of the road scenarios, getting about the tails, and people focus on the immediate impact of climate change, but do not go for the knock-on effects in economic growth or violent conflict of things like that. This is actually the same point I made before. But yes, this is what we have. And in the time-honored tradition of decision analysis, we should work with the information that we have, right? Rather than speculate about the information that we could have had and the decisions that would have followed from that information. We should work with what we know. And if you think this is a load of rubbish, then you should work on and add additional data points to this. I've been talking about the total impact of climate change. This is very interesting and gets a lot of people excited, but unfortunately is not necessarily what you should be looking at. There is missed, that message is missed by some people, including high-profile people, like certain statistics professors from Columbia. Really what matters for decision analysis and for decision making is what happens at the margin. Something that has been drilled into your heads ever since you started studying economics. So we should focus on the marginal impact. Why should we do that? Well, if you want to maximize something, then what matters is the first order condition, first and foremost. And first order condition always says take the first partial derivative and set it equal to 0. Right? So what matters is what matters at the margin. More prosaically, climate change is a long-term problem. Climate change is a global problem. So if you're in charge of a country, say you've been elected prime minister, then typically you're in charge for 4 or 5 years until the next election. And for a long-term problem within those 4 or 5 years, you simply cannot solve the climate problem. And typically, people are elected to run part of the world rather than the entire world, right? And also a country like the Netherlands or the UK or Germany or what have you simply cannot solve the climate problem. You cannot take away the total impact of climate change. The only thing you can do is change your emissions during your term in power by a little bit. Right? So what matters is what happens at the margin. If we emit an additional ton of CO2, what would be the additional damage done? The way to calculate this is to run a scenario of greenhouse gas emissions, calculate the impact of climate change, for instance, using the function that you see here, and then run a slightly different scenario of greenhouse gas emissions, calculate the impact again, take the difference between the two estimates of the impact, and discount the whole thing back to today, normalize it with the change of emissions that you're put in, and that is your incremental impact of the extra CO2 that you put into the atmosphere. And that is a reasonably good approximation of the marginal impact. You actually can try and take this derivative analytically, but you will fail, hopefully, unless you created such a caricature of the problem that you can take the derivative, but if you have a decent representation of the problem, you can't take the analytical derivative, regardless of what Golosov and people might tell you in esteemed journals like Econometrics. This is a normative concept in two dimensions, or in two ideas of the word. Essentially, this is very close to the conclusion. Like, this is essentially the additional damage done from an additional ton. And if you recall your micro, then this is the carbon tax that you want to impose in order to internalize the externality. So this is the conclusion. So in that sense, it's normative. It tells us how much we should spend on climate policy, or how much we should raise the price of energy. And it's also a normative concept in the sense that what we do is we value impact over a large period of time and discount them back to today. So whatever the result will be depends on what we think the discount rate should be. We value impacts over a large number of countries, add them up to a global. So it depends on what we think the relative impact on somebody from the Netherlands or somebody from Bangladesh should be. And also we valued a lot of impacts that the prices are actually not at all obvious. We put values on nature, we put values on health. And that also reflects what we think is good and proper. So it's also a normative concept in the sense that it reflects our values. It tells us what to do, but it also depends on what we think our values should be. There's been, last time I counted, this is now almost a year ago, 753 estimates of the good tax, the marginal damage cost, the social cost of carbon. And for the moment, I use these terms interchangeably. You may think that is odd. Right? We have 30 estimates of the total impact of climate change. So how can there be 750 estimates of its first partial derivative, the social cost of carbon? Economists, definitely economists with PhDs, know how to take a derivative, right? So this is not some sort of calculus error. The reason is that the impact function that I showed you actually cannot be directly applied. And actually, what you saw was 30 or so primary impact estimates of climate change, and they're all independent. And the curve that I showed is just what I think the curve should be. But other people think that this curve looks differently. And essentially, you have only a limited number of points to which you can calibrate this curve, and different people have made different choices as to what the impact curve should look like. So that is one additional degree of freedom that is introduced that explains the difference why there are so many partials for so few totals. The impact of climate change obviously depends on what you assume future emissions to be. another degree of freedom that is introduced. It depends on how the atmosphere responds to those emissions. It depends, or the impact of climate change depends on the future size of the economy, how fast population growth would be, how many people are affected, and so on and so forth. That introduces additional degrees of freedom. And all of this explains why we go from 30 estimates of the total impact to 750 estimates of the marginal. And actually, of those 30 total impact estimates, most have been ignored by the social cost of climate literature, and they actually derive from 4 or 5 of the impact estimates that I've shown only. If you have 750 estimates of something, you can do fancy statistics, right? You have data to play around with, and that is what happens here. The curves that you're looking at are the kernel density estimates, or are the kernel density estimates of the cumulative density function. And the way to read this is to include all estimates. Then there is a 27% chance that social cost of carbon is negative. This then implies that there's an 83% chance that it's positive, and there's a 50% chance that it's greater than $300 per ton of carbon, and that also then implies that there's a 50% chance that it's smaller, right? So this is the CEF. Now, if you have 750 estimates, you can also do sample splits, and then you actually start learning something rather than different people have estimated different numbers. Very insightful. And the primary sample split is as to the rate, the pure rate of time preference. So I'll get back to that next week. Essentially, the utility discount rate and your money discount rate is 2% higher. So if you use a 5% discount rate, then you end up in the red curve. If you use a 3% discount rate, you end up in the blue curve. If you use a 2% discount rate, then you end up with the green curve. The higher the discount rate, the less we care about the future. If we care less about the future, then we care less about climate change. It's primarily a problem of the future, and that is exactly what you see. The median estimate is 475 for a low discount rate, goes down to 150 for a medium discount rate, and goes to 35 or so for a higher discount rate. That is exactly what you would expect, right? And we'll get back to that at length next week. There's another thing going on. If you use a higher discount rate, the uncertainty is much narrower. The red curve looks like a proper CDF. It starts at 0 and it ends at 1. The green really is a CDF, but it doesn't look like that at all, right? I mean, it doesn't want to start at 0. You have to go far to the left, and to get to 1, you need to go far to the right, and you probably end up at the Amsterdam Tibet, right, before it reaches 1. That's not the Amsterdam Tibet, that's about the Dar es Salaam, right? Why is that? The higher the discount rate, the less we care about the future, and the less far we need to peer into the future, because it just becomes irrelevant. But with a low discount rate, you need to peer far into the future. And the further you look into the future, the more uncertain things become. You have a reasonable idea of what's going to happen this afternoon, a reasonable idea of what the world will be like in 20 years' time. You don't really know what the world will be like in 200 years' time, or in 2,000 years' time. And if we use a discount rate that is close to 2%, we need to look into the far future. The infamous Stern review advocated the pure rate of time preference of 0.1%, which means that you need to evaluate the future for the next 12,000 years. Events that would happen 12,000 years from now would still influence your marginal cost estimate. You can imagine that if you look 12,000 years into the future, pretty vague about what the world will be like. So that is the explanation why the uncertainty tightens for higher distances. These are the CDFs. Here are some numbers. This is given here for a 3% discount rate. $27 per ton of carbon. This is not a very meaningful estimate to most people. $27 per ton of carbon is roughly equivalent to €5 per ton of CO2. There's two transformations there, which is roughly equal to the price of emission permits in the European market. So by happenstance, the current price of greenhouse gas emissions in Europe is equal to what Pigou said it should be. If you impose a carbon tax, then emissions would fall. And if emissions would fall, climate change would be less pronounced, and the impact of climate change would be less. We would expect the impact, the marginal cost to fall, and that's exactly what we see happen here. The next slide is just the same, but prettier. So let's focus on this one. That's a bit weird. So if you impose a carbon tax, then you would expect the impact of climate change to fall, and therefore the social cost to come down. And that is actually our proper estimate of the Pigou tax. The Pigou tax is, of course, evaluated along the optimum, not along some arbitrary scenario. And a no climate policy is in fact an arbitrary scenario. And what you see here is for the studies that use 3% pure rate of time preference, the split between, or the difference between the Pigou tax, that is the social cost of carbon evaluated, the marginal damage cost evaluated along the optimal emission path versus the social cost of carbon, where the marginal damage cost is evaluated along a no climate policy. You see that there's a subtle difference. You see that there's indeed a slight shift to the left. That is, the Pigou tax is slightly lower than the social cost of carbon. It's not a big difference. It's not statistically significant in any way, but it is a subtlety that of course, somebody who claims to have a master's in economics should be aware about. The Pigou tax, properly defined, is the marginal damage cost in the optimum, and not arbitrary. And that is the tax that we should impose on our emissions, rather than the social cost of carbon. You also see that just a little bit of tax it takes away a lot of the tail. The bigger difference between the red line and the green line is not so much that the motor shifted slightly to the left, but it is that you take away a lot of the bad stuff that might happen, the low probability and high impact stuff disappears rapidly with the application of a small carbon. So to sum up, talked about the impact of climate change on welfare. The benefit of climate policy is, of course, the impact of climate change that you avoid. I hope I've made clear that it rests on many assumptions and stuff that is fairly uncertain. And I also hope to have made clear that this is not a positive estimate. This is not an objective description of the real world, but it's a mix of objective descriptions of the real world to the best of our ability, but also a lot of value-laden assumptions on top. And the result is a mix of the two. And don't ever be fooled into by somebody who claims that they know the truth. Right? Okay, we're going to break for 10 minutes, and then I'm going to continue with the distribution of these impacts and what that means for climate policy.